Hidden beneath a thin roadway are forces as large as mountains. Over thousands of feet, suspension bridges balance millions of pounds of live load, wind, and earthquakes with just a few primary elements. This is a story of tension and compression, where flexibility is strength. Start with the main cables, flexible, tensile members that hang in a catenary curve between towers. They carry almost all vertical load as axial tension. The towers act in compression, channeling that load down through foundations into the earth. Anchorages hold the cable ends, converting horizontal pull into bedrock reaction. The deck, a relatively light plate, must resist bending and twisting. A stiffening truss or orthotropic deck redistributes concentrated vehicle loads across the span. Suspender rods or hangers connect the deck to the main cables, often in pairs or continuous systems, with redundancies so one failure does not collapse the structure. Every component is sized to handle peak loads plus safety factors, often 2 to 3 times expected extremes. In this chapter, we map the structure, towers, cables, suspenders, deck, anchorages, and expose the invisible flow of forces. By the end, the bridge will seem less like a single object and more like a balanced machine, a cathedral of tension and compression engineered to stand for generations. Everything begins as raw rock and carbon. Iron ore, limestone, and coke are transformed in blast furnaces and electric arc furnaces into steel. For a suspension bridge, we need high-strength structural steel for towers and rebar-strengthened concrete for foundations and anchorages. Steelmaking controls chemistry precisely. Carbon, manganese, silicon, and microalloying elements tune yield strength and ductility. Plates and shapes are rolled to size, flange widths and web thickness measured to the fraction of an inch. Meanwhile, for main cables, manufacturers draw wire from billet through progressive dies, reducing diameter in stages until they reach a few millimeters to a few tenths of an inch. Each wire undergoes heat treatment and surface treatment, often bright anneal and then galvanizing to provide corrosion protection. Concrete arrives as a recipe of cement, aggregates, water, and admixtures to reach compressive strengths from 4,000 to 8,000 pounds per square inch, sometimes more for special mixes. Steel and concrete meet in composite decks and anchorages. The logic is simple. Towers must resist buckling under compression, cables must resist tensile rupture, and foundations must transfer enormous loads into competent ground. Quality control begins here. Chemical analysis, tensile testing, and non-destructive inspections ensure raw materials will behave predictably under decades of load cycles. Towers are the vertical backbone. They must be tall, stiff, and light enough to stand during construction. Fabrication starts in steel shops where plates are cut, beveled, and welded into box sections, I-beams, or built-up columns. Laser and plasma cutters slice steel to tolerances of a few millimeters, and welders follow procedure qualification records to deposit controlled weld metal. For concrete towers, slip-forming or climbing formwork pours continuous pours at rates of several feet per hour, with embedded rebar cages that transfer shear and moment. Steel towers often arrive in sections, 50 to 200 feet long, bolted and then welded on site. Erection uses crawler cranes and synchronized strand jacks to lift heavy segments, each lift planned with crane charts, load paths, and safety factors. Once erected, towers are aligned within inches over hundreds of feet using survey instruments and total stations. Saddles at the tower tops carry the main cables and are machined to smooth curvature to prevent stress concentrations. Bolted connections use high-strength bolts pre-tensioned to a specified torque or measured via calibrated hydraulic tensioners. Every fabrication step reduces uncertainty because a misaligned tower changes cable geometry, and cable geometry dictates the whole bridge's behavior. A suspension bridge is only as strong as its foundation. Foundations transfer loads deep into the earth, often to bedrock hundreds of feet below water. Construction methods vary: drilled shafts, driven piles, open caissons, or pneumatic caissons that allow workers to excavate below water by working in compressed air. In marine settings, cofferdams create dry work areas where massive concrete gravity anchorages are cast. Anchor blocks are huge, often thousands of cubic yards of mass concrete, designed to resist horizontal cable tension by weight and friction against rock. Deep foundations use reinforced concrete piles or rock-socketed shafts that achieve end-bearing and skin friction. Scour protection around footings uses riprap, articulated concrete blocks, or engineered mattresses to prevent erosive currents from exposing foundations. Geotechnical investigation precedes all work. Boreholes, standard penetration tests, and cone penetration tests determine shear strength, allowable bearing, and settlement estimates. Design uses factors of safety and serviceability limits to keep settlement within inches over decades. The logic: send the concentrated forces from towers and anchorages into competent ground so the whole system behaves as designed under millions of cycles of live load and environmental forcing. The main cable is a rope made of thousands of wires. The process begins with wire drawing. Steel rod is pulled through a series of dies, each stage reducing diameter and increasing tensile strength through cold work. Wires are cleaned, lubricated, annealed if needed, and then galvanized or epoxy-coated for corrosion resistance, coatings measured in tens of micrometers. Cable spinning on site uses either continuous spinning machines or parallel strand methods. In continuous spinning, a traveler car pulls individual wires back and forth across the span, wrapping them into the forming block at the saddle and compacting them with hydraulic presses until a circular cable is achieved. Typical cables contain from 10,000 up to 40,000 individual wires, depending on span and design, each wire contributing to redundancy. After spinning, wires are compacted, bound with wire wrapping, and often enclosed in a protective sheath and injected with grease or sealed with epoxy to prevent moisture ingress. Finally, cable bands and saddles are installed to collect wire bundles into strands for suspender attachment. The logic of spinning: many small wires share load, so an isolated fracture is harmless, and the cable becomes a flexible, high-capacity tensile member engineered to carry the whole deck between towers. A suspension bridge's deck must be light but stiff. Left unsupported, a long deck would flutter and sag. Engineers use stiffening trusses, box girders, or orthotropic steel decks to spread local vehicle loads across the entire width and length. An orthotropic deck pairs a thin steel plate with longitudinal ribs and transverse crossbeams, like a waffle, creating high bending stiffness with low weight. Composite decks combine steel with concrete wearing surfaces for durability and vibration damping. Connection details matter. Shear studs weld to the steel plate to create composite action, and expansion joints at bearings allow thermal growth of several inches. Bearings themselves may be pot bearings, sliding bearings with Teflon, or elastomeric pads, each allowing controlled rotation and translation. Drainage, utilities, and barrier attachments are integrated into the deck, and aerodynamic shaping reduces lift and vortex shedding. During fabrication, tolerances for deck flatness are within a few millimeters over tens of feet. The goal? A deck that feels solid to traffic, resists fatigue from millions of axle loads, and works with the cable system to keep stresses in safe ranges under the wide variety of live and environmental load combinations. Erection is choreography. After towers and cables are ready, workers hang the deck using suspenders, then tension the system into final geometry. Temporary catwalks and cable templates guide the placement of hangers at precise spacing. Hangers may be fixed length or adjustable. Adjustable rods allow incremental leveling. As deck segments are lifted, hydraulic jacks used in concert apply precise tension to suspenders and main cables. Engineers monitor sag, deck camber, and cable force with load cells and surveying instruments, making adjustments in fractions of an inch. The sequence follows staged loading rules. Sections are balanced across the towers to avoid asymmetric loading. Cable tensioning uses calibrated strand jocks that pull strand bundles to target force values, often measured in thousands of kilonewtons, then anchored by wedge grips. Once deck segments connect, the structure begins acting as a continuous system. At that point, final stress redistributions occur and the bridge reaches service geometry. Temporary supports are removed only after engineers confirm stress, alignment, and deflections are within calculated limits. Precision here is essential. Imperfect geometry changes live load distribution, increases fatigue, and shortens lifespan. A long, flexible bridge is a giant sail. Wind excites vortex shedding, causes flutter, and can amplify movements from traffic. Engineers use wind tunnels and computational fluid dynamics to understand aerodynamic forces. Deck cross-sections are shaped to reduce lift and control separation. Small lips, fairings, and ventilated grates change airflow patterns. Tuned mass dampers, viscous dampers, and cable dampers dissipate energy. Tuned mass dampers are heavy masses attached with springs and dashpots tuned to a target frequency. Against a resonant excitation, they absorb motion. Cable dampers, small metallic weights with friction or viscous elements, break up standing waves along hangers and prevent fatigue. Fatigue is a primary design driver. Details at connections concentrate stresses. Designers limit stress ranges and specify fatigue life in millions of cycles. Ice, temperature cycles, and traffic-induced vibrations are modeled as load spectra to size members and choose materials with adequate endurance limits. The logic: control energy flow. If the structure can't dissipate or redirect aerodynamic and dynamic energy, small oscillations can grow into destructive motions. Redundancy and damping keep the bridge from turning into a tuned instrument of disaster. Quality control treats every component like a life-critical device. Wire samples go to tension testing rigs where technicians pull until yield and rupture, recording yield strength, ultimate strength, and elongation. Non-destructive examinations include ultrasonic testing for weld defects, magnetic particle inspection for surface cracks, and radiography for internal flaws in critical castings. After construction, proof loading simulates service and extreme loads. Hydraulic jacks or calibrated weights apply loads to the deck while engineers measure deflections and strains using strain gauges, load cells, and displacement transducers. Cable inspection uses acoustic emission monitoring and electromagnetic methods to detect broken wires in a main cable without dismantling it. Corrosion protection systems receive adhesion and thickness tests, coating thickness measured in micrometers, and holiday detection used to find defects. Fatigue checks use historical traffic spectra to project remaining life. For bridges in seismic zones, isolators and dampers are tested to specified cycles and displacements. The logic is verification. Prove the bridge meets design assumptions and monitor it throughout life using sensors and periodic inspections to catch the first sign of degradation before it becomes a hazard. A suspension bridge is a living structure requiring care. Design life often targets 100 years with regular maintenance cycles, repainting or recoating main cables and suspender systems, replacing bearings, and patching decks. Monitoring systems, tilt meters, strain gauges, anemometers, and cameras feed real-time data to maintenance managers who schedule interventions. Corrosion control continues with cathodic protection, grease injection into cable interiors, and regular inspection of anchorages and joints. When fatigue cracks appear, repairs use methods like local reinforcement, cold-sprayed metal overlays, or complete hanger replacement. Major rehabilitation may upgrade seismic resilience with base isolators or retrofit decks to orthotropic sections. The design logic emphasizes inspectability and replaceability. Suspect elements are made modular so technicians can replace parts without shutting the bridge for months. Finally, the bridge is an engineering statement, a precise balance of forces, carefully chosen materials, and repeated testing. It transforms raw earth, iron ore, and labor into a span that connects communities. Generations feel that engineering in each crossing, an object that is part machine, part monument, and wholly an achievement of applied physics and craftsmanship. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.